All right, let's start out with talking about high-speed electronics trends and challenges. It's the agenda I want to cover in the introduction. So I want to look at some of the business drivers in high tech and some of the current trends that we're seeing in the company. I also want to look at some trends in simulation that we're seeing and how problems are being solved. I want to cover some of our initiatives we have in 2024 around electronics, some of our new workflows, for example. And then I want to look at simulation of data channels in particular. And finally, I'll take a look at some current reference designs we're putting together to help demonstrate our capabilities. So what are the current industry drivers we're seeing in high tech? Well, these are some of the ones that we've identified recently, but these are not new. These have been going on for a few years now. Some of them have become more important than others over the last year or two. So what have we got? We've got innovation and delivery. We know in high tech, when you think about smartphones, smart devices, computers, data centers, and so on, innovation really is key. Companies have to innovate regularly. They often have a schedule of new releases, often once a year or even more frequently than that. And they have to deliver on time. We know that certain companies have a certain month or even a certain date in the year when they deliver updates. So they can't miss those deadlines. It gives a bad impression to the market if they were to miss those types of deadline. So innovation and delivery, very, very important in high tech. We also know that regulatory compliance has become increasingly important in recent years. These kind of problems have even made the mainstream news, because what happens if a company does not meet compliance standards for a particular country, they can lose their permit to sell those devices in that country. So this has become very critical. There are a lot of different standards around the world, and every device that a company sells, every variant, has to meet the specific geo requirements. So many different variants, many different geo requirements. This can be quite a headache to resolve. Keep going around clockwise here, everything connected. We know that every device that we carry, all of our smart devices, they have to be connected. Some of them are connected around the home. Some of them connect as we're outside the home, as we're walking around or attending events, as we're working on the train, and so on. And we expect increasingly for everything to be connected, for us to be connected to the world at all times. Now, there are a number of challenges around that we'll cover to some extent in this presentation. Battery performance, we know, is important. There have been a number of stories around, or high-profile stories, I should say, around battery failures. So we know that the robustness, the safety is important, but we also know the capacity and the number of cycles that you can charge the battery at is also important. Robustness, this has become a very important metric for OEMs over the last few years. It's seen as a sign of a quality product when it maintains its integrity after being dropped or sat on or immersed in water. So you can see here, obviously, this is a cracked screen, which used to be a lot more common than it is these days. I think phones have generally become more robust, and it's certainly a goal of the OEMs to increase that robustness going forward. And finally, digital infrastructure. So we see that the backbone of a lot of what we do today is based in the data center. A lot of our data is stored there. So the safety, the integrity of those systems, the always-on nature of digital infrastructure has become very important as well. So that's some of the high-tech general challenges. Some of these we'll cover today, some of them we won't, because these cover all sorts of areas, but we're really going to focus on the electronics challenges today. So what do we see in trends generally? Well, we have seen recently that devices, and particularly the consumer smartphone, has somewhat plateaued in terms of its growth. So there was, explosive growth over the last few years that has somewhat leveled off. That doesn't mean innovation isn't still happening. It is, but the sales of smartphones have certainly leveled off. We've also seen challenges on the equipment side, things like public networks. I think 5G was expected to grow faster than it actually has. So that's also created some challenges among the equipment manufacturers and the tower companies as well. On the other hand, we've seen growth in quite a lot of other areas in the high-tech space. So we've seen the private networks becoming quite interesting to companies. So this is a closed network that's private to a particular company and has certain advantages because of that. We've seen AR, VR devices grow, and recent releases you may have heard of have really been pushing the boundaries of that. But there's a lot of physics going on inside there, a lot of mechanical concerns, electronics, antenna issues, and so on to get right. Digital infrastructure, as I mentioned, the data center and other kinds of high-tech infrastructure is becoming quite important. Electronics, the back-end electronics to all of these systems is what we're going to focus on today. And that continues to be very important and continues to grow as electronics get faster, as processors evolve to become faster, and all of the supporting electronics around the processor become very important. We've also seen wearables, not just in high-tech, but also in life science and healthcare, become important as well. And then finally, the battery. So battery really is a mainstay of high tech. I would say we're relying on batteries a lot or increasingly to keep our devices going. And there's a lot of innovation going on around the battery to continue to improve that technology. What about in simulation itself? So, here at SIMULIA, as part of Dassault Systems, we're interested in doing physics-based simulation of all of these devices and their component parts. And of course, this covers things like structural simulation, electromagnetic simulation that we're focused on today, but also fluid or CFD simulation, thermal simulation, and pretty much every kind of physics you can think of. So in the simulation domain, we've seen that design of experiments and artificial intelligence, machine learning, is starting to become very important. And this is something we're certainly exploring in terms of really exploring the full design space, and not just the design space in one domain like structural simulation, but including all domains as well. So you get a complete picture and you end up with the optimal solution to the problem. In the middle there, we have recently been exploring this ModSim approach, modeling and simulation, and we'll talk in more detail about that later. But really, this is a holistic approach to simulation, and it's an end-to-end approach as well. So not just simulation, but also going all the way from requirements to the end product. We'll have a demonstration of that a bit later. And then finally, cloud and high-performance computing. So Dassault Systems has a cloud-based infrastructure, and all of our solutions now run on cloud. And this is an option for you. It's becoming quite important because with the acceleration and the availability of new hardware and the efficiency of new hardware, companies don't always want to keep up with those trends and maintain these hardware infrastructures themselves. So using the cloud, which is typically always at the leading edge of hardware capability, is becoming an increasingly important option for a lot of companies. All right, just want to touch on ModSim a little bit. As I said, we'll have a demonstration a bit later. But we see this as a sort of a key approach to simulation. It puts simulation really in the center of what you do in order to get a product to market. And what we mean by that is we include not just the simulation, where you may get a file, say, from a designer, a CAD designer. He maybe emails that to you or puts it on a shared drive to you. You run the simulation, and then you say, that's it. Maybe you run some optimization. Once you've optimized, you pass it back to the designer. That's the typical way we used to see simulation. But now we have a different approach where we take into account all of the project management capabilities that we have on the 3D Experience platform. So this is the sort of bigger part of Dassault Systems, if you like. We look at the requirements for the product, or the new product, in terms of all of its KPIs, all of the metrics, all of its capabilities, the compliance that I mentioned earlier, for example. We include things like validation studies, certification, processes and automation, change management, and even things like collaboration and analytics. So the platform is a globally web-based platform that allows you to collaborate on projects too. And the really important thing is that it's not file-based anymore. It's platform-based. So that means there is a single source of truth. When a CAD designer changes the design, the simulation engineer immediately sees that change and can act upon that change. And we'll get into details of this a bit later, but we see this as a bit of a paradigm shift in the way simulation is viewed as part of the end-to-end product process. Just want to touch on why we see virtual twins or physics-based simulation as being so important in high tech. And this goes back to some of the challenges I mentioned earlier. So, we're seeing increasing complexity in devices, increasing density, just-in-time innovation, as I mentioned, getting those release dates as close to the correct date as possible. We see a number of test scenarios that are actually not possible to do in the real world because it would just take too many resources. As an example here, phones are typically put through a drop test scenario. They have to be dropped at different angles with different materials, with all of the different variants. And that would just take an extremely long time to do in the lab. So being able to do that through simulation really does save an enormous amount of time. And it just wouldn't be possible to get the throughput of scenarios done without simulation. So we've got to meet a number of KPIs as well, as I mentioned, compliance KPIs, really all the way up to the first prototype. So the goal for the OEM is to get that first prototype working at the first go. That's a huge challenge, but simulation, in fact, can help the OEMs to achieve that on the first prototype. And then going beyond that, beyond the product release stage, we want to make sure that the in-service performance is good as well. So late-stage problems, in other words, don't show up later. There are some well-documented cases of late-stage problems in devices, which have called recalls and warranty concerns as well. Okay, I wanted just to look briefly at some of the electronics initiatives that we have this year. This is in my team and other parts of the company. We are looking in depth at electromechanical design for components and semiconductors. And this could include things like MEMS devices, haptic devices, touch screens, ball grid arrays as part of a semiconductor package. And in the middle there, you can actually see a structural simulation of a PCB. That's obviously highly exaggerated, but vibration of PCBs is also a concern as well. So that's one of our initiatives, to look at all those electromechanical type problems and connected physics. We also want to look at high-speed channel design. And this is something we'll talk about quite a bit today, going all the way from the cable to the chip package on the device that we're looking at. Now, this is important because as speeds increase, as Wi-Fi speed increases, cellular generations increase the speed, we need to keep up with that sort of external requirement, if you like, with the internals of the device. So every transition that the data has to go through has got to be managed. In other words, as you go from the connector to the PCB or to the flex circuits to the chip package, each of those transitions has to be carefully designed so that you're not losing speed through those connections. And we'll talk in depth about this a bit later. So that's another one of our initiatives. And the last one is really all concerned about ModSim, as I touched on earlier. So that is sort of the holistic approach to simulation, including a lot of the other brand products within Dassault Systems, such as the CAD tools that we have from CATIA, from SolidWorks, and in addition, not just our internal CAD tools, but other CAD, perhaps from other providers like Siemens or PTC as well. Now, some of the challenges in electronics are regarding the sort of back end or the digital back end design of systems, if you like. In SIMULIA, we talk quite a lot about antenna systems and how they're critical to communication between devices or to some central infrastructure. And obviously that's very important, and we have good solutions for that. But just as important is the back-end electronics and the speed it operates at, as I mentioned, the reliability and the certification of those electronics as well, because they can also cause interference and unwanted emissions that would have been covered in the EMC day recently. So, the focus of today is really to look at these back-end systems and what the challenges are and why simulation can really help with the problems that might be encountered. And what you're seeing here, by the way, is a schematic of a typical modern smartphone where you have, the analog front end. In other words, this is the systems that actually transmits the signals over the airwaves, and maybe you have millimeter wave, 5G millimeter wave, and then you've got the sub-6 GHz cellular bands in addition to that. And then at the back end, you've got things like obviously the processor, which is not shown here, but then you've got the modem, RF transceivers, maybe even antennas on chips, all in the back end of the device. So what are some of the challenges, and how can electromagnetic simulation really help to solve these types of back-end digital problems? Well, data channels are very complex, as I mentioned. They go all the way from the cable, the connector, through all the different transitions that I mentioned. They're very complex channels to manage and to get right. You've got to get the signal integrity right. You've got to make sure the emissions are correct below a certain threshold. You've also got to make sure they're not susceptible to interference from outside. So there's a lot of different challenges you have to manage. Now, the higher the data rate you want to put through these types of devices, the higher bandwidth those channels have to support, which means higher frequencies have to be supported. Okay, so those channels have to support the higher data rates that you want to put through. So this wired digital data that we're talking about, it's still an electromagnetic problem. As I mentioned earlier, people often think of antennas as electromagnetics, but really these wired problems, these signal integrity problems, at their core, they're also electromagnetic problems as well. So this means that electromagnetic solvers that we have within CST Studio can really help to characterize and optimize these channels, in fact, very nicely. And in fact, the efficiency of these solvers means you can actually simulate a complete channel, not just parts of the channel in isolation. Just want to mention one important topic, which is simulation versus measurement, because this topic often comes up when we talk to customers, particularly customers who are not so familiar with simulation and what it can do. So when you look at the typical hardware prototype, all the effects are included, of course. When you put the device into an EMC chamber, you set it up, as it might be transmitting or receiving. And as a result, you get a typical of a pass-fail information. But the analysis of the cause of that pass or fail are often hard to understand, because you're only seeing the sort of whole device in operation. So if you look at the virtual twin or the simulation approach, that can give you much more information about the root causes of problems, because only the parts of the system are simulated. Okay, there's actually a lot of unknowns there, but because it's broken down into its integral parts, you can really identify where the cause of the problems might be coming from. We don't typically get a pass-fail for the whole system, but that's okay, because that's where you have the testing requirement at the end of the simulation process. Okay, so that sort of helps to understand why we really need both approaches, right? We need the virtual twin, the simulation approach, but we also need the hardware prototype and the test environment approach as well. So what you can see on the right here is actually a PCB from a reference smartphone that we've developed internally, which I'll talk about in a second. But on the left, it just gives you an impression of some of the speeds that we are seeing in typical channels inside a modern device. So this shows you how USB, the USB standard has increased in speed over the years, all the way from USB 1 up to USB 3. And of course, USB 4 is also in development at this time. So as we go up in speed, as I mentioned, you do have increasing challenges, things like crosstalk, each junction, each transition of the trace through the device becomes more critical at high speed. You may have increased EMC problems as well. So certainly simulation of these channels becomes extremely important in order to get this right. So our time domain solvers that we have built into CST also make it possible to simulate the complete device, right? So not just that PCB that I showed by itself, but that PCB integrated into the complete systems of the phone, placed in its installed position, which can be very complex, of course, with a smartphone with thousands of components. The other nice thing is that the time domain solver gives you a broadband response. So you can see the interaction between all the channels. This is actually showing the differential common mode S parameters through this device, through all the different channels that we have. So you can see how the channels are affecting each other very nicely through these S parameter type results. Just to give you a quick overview of all of our capabilities within SIMULIA for simulation of this kind of device, we typically break it down into pre-layout and post-layout analysis. So when you're looking at pre-layout, you may be looking at an individual transition or a stub or a via, for example, going through a PCB, and you may want to optimize that individual transition to make sure the impedance doesn't change through the transition, to make sure that the broadband S parameter looks good. Once you've done that, once you sort of optimize those individual transitions, then you may want to go into the left-hand side of this picture in the post-layout analysis. And here is where you probably want to optimize the layout, maybe use some design rule checking, do a full 3D signal and power integrity analysis, and then sort of at the end of the process, you may want to look at some thermal simulation as well. And we'll cover a lot of these topics as we go through this presentation. I should also point out at the beginning of the process, getting the data or the layout data, extracting that data and getting it into the 3D domain for simulation is an important part of the workflow. It's a very important part of the workflow. If you don't have this, going through a 3D approach, a CAD approach really is very inefficient. So being able to import stack-up data from layout tools like Cadence or LTM and others really does make the workflow quite straightforward. And the way it works is you bring those layouts in, you can adjust the materials, you can adjust the stack up, as you can see here with a very nice dialog that we have set up. And there's a number of other adjustments you can make here as well before you do that full 3D extraction and then simulation. Something quite recently we've introduced, and this is really a benefit of having multiple physics solvers within the company under one umbrella, is we've connected ECAD to MCAD. So we already had a very nice solution with ECAD within CST Studio, where you can bring layout in, you can run an electromagnetic simulation, as I've been discussing. But now we're able to take that layout and direct it towards Abacus, to our structural solver. And we've seen here, this is quite important because of a number of advances in the types of PCB we're seeing, including multiple stack-ups, things like flex PCBs, unwanted resonances on the board, which are causing vibroacoustic issues or other concerns. So being able to have this structural simulation very seamlessly connected to the layout import and the electromagnetic simulation is a very nice feature to have, and we've seen a lot of interest in this from PCB designers and OEMs. Just very briefly, I want to touch on the semiconductor side. So as well as the PCB side and associated electronics, we do see an increase in complexity in semiconductor packaging. Quite a lot of innovation going on here, as I mentioned at the beginning, in terms of the trends, things like ball grid arrays and new advanced packaging coming to the forefront. So being able to model the signal and power integrity, also the EMC issues with semiconductor packaging becoming important as well as the power and thermal management associated with those. And we do have a workflow set up that's quite nice for chip package simulation. So again, taking the layout import from a tool like Virtuoso, for example, Cadence Virtuoso, doing the extraction and the simulation. We also have macro modeling capabilities that I'll touch on in my my final slide next. And then you can do also a back annotation back to the layout tool and do things like running a system simulation in Inspector or other system level tools. And yes, the macro modeling capability, this is quite an important feature for electronic design automation, being able to take a high-speed interconnect, for example, either from simulation or from measurement, in fact, getting those S parameters, being able to create a black box macro model, which is guaranteed passive and causal, and then using that black box in a system simulator further down the line. But being able to generate the causal and passive model, the guaranteed causal, guaranteed passive, is very important for system designers, so that when they run their SPICE simulations, the whole model doesn't blow up. This is a very nice capability that we have within CST Studio. So that's pretty much it. I just want to round out this presentation by showing you one of our reference designs. This is actually not the latest iteration of this. This is a little bit older, but it does show that we are creating reference designs that we use to demonstrate the capabilities that we have, both to our customers, but also with the help of our customers to put these together. So we know that IP is a major issue in high tech. Customers are not going to give us their models. This is typical, or even the components, that we don't know the details of the components. So we have to sort of put it together with the knowledge that we have, the public knowledge that's available, and also with some guidance from our customers. And we've done that. We've created a fully featured smartphone in software, includes 5G antenna systems, Wi-Fi, LTE, pretty much everything you can think. It's got a PCB in there. It's got all of the subcomponents, the battery, the IC package, and so on. You can even see the connector systems and the cable on the right-hand side. So having this full capability really helps us to identify challenges and provide very nice workflow solutions to those challenges that we see. Okay, that's it from me.